We can also use the odds ratio to interpret that fitted slope if our predictor is quantitative. The thing is, it's a little bit challenging because if we're in the original probability scale in our response variable, you picture that S-shaped logistic curve. As we move along the horizontal axis, as the x changes, the slope of that curve changes as well. If we're in the log odds scale, then we have a linear function, but as we were saying in the last video, it's difficult to interpret. What does it mean to say we have a typical change in log odds when the input goes up by 1? But one thing that we want to just remember is that when we have that constant slope in the log odds scale, we're talking about a constant odds ratio. So as we move along the x, even though the x value is changing, that odds ratio is not changing. So we have this data set, putts.csv. This data comes from a golfer who was attempting putts at different lengths from the cup, 3 feet, 4 feet, 5 feet, 6 feet, and 7 feet from the cup, and keeping track of whether he made the putt or not. So notice that our explanatory variable, the length of the putt in feet, is quantitative this time, and our response variable is still binary categorical. 1 we're going to code as success, he made the putt. 0 is failure, he missed the putt. Now the data set is not in summary form, it's raw data, but you can sort of create the summary table that I have, although not all at once, by using this code. So this first table command basically gets the first 3 rows of the table together. And then this margin.table creates the totals for each length, total number of putts for each length. And then the mean command here is getting you the proportion of success. And then, finding the odds by taking the p hat over 1 minus p hat at each length. And then, could use orange. The logit p, just finding the log odds there, gets us that empirical logit. All right, so in this case we have 5 different values of the explanatory variable instead of just 2. So we can create odds ratios to compare any 2 lengths. So, for example, if we want to compare the odds of making a 4-foot putt to the odds of making a 3-foot putt, we take the ratio of those odds of success, and we get 0.575. So we're saying the odds of making a 4-foot putt, that's the value that was in the numerator, are about 57% of the odds of making a 3-foot putt. And of course, we could have done the ratio in the other direction, but we're just going to do this systematically, going right through the different lengths there. Now the code I gave here in R, I just want to show you for one example. So in the first line of code here, we're finding the difference in log odds, and again we're just working our way through the different values. So this would actually give you the empirical logit at 4 feet minus empirical logit at 3 feet, and then the next value would be the empirical logit at 5 feet minus the empirical logit at 4 feet, etc. Okay, but basically, if I just use the first pair, 1.043 minus 1.598, that's the first value that's going to come out of this top command here. And that value is negative 0.555. And that is, remember, the log of the odds ratio. So that's the log of this 0.575. And if we exponentiate, which is what the second line of code is doing, right, this would be doing e to the negative 0.555, and that would actually get us the 0.574 or 0.575, a little rounding error there, right? So we're exponentiating the difference in log odds, but the difference in log odds is the log of the odds ratio. When we exponentiate the log of the odds ratio, then we get the odds ratio, right? Okay, and then so this last line here is just calculating the odds ratios one after another. So can kind of, that just does it automatically, but I just wanted to remind you of how that's being computed behind the scenes. All right, now in this case, we fit the logistic model, and we have just the regular made versus length, because the data, again, was not in summary form. It was just in raw form with the GLM command. And we have this constant slope of negative 0.56614. And as it says up above, if we exponentiate that slope, e to the negative 0.566, we're going to get a constant odds ratio of 0.568. So in the middle row in this table, so we have 4 feet to 3 feet, 5 feet to 4 feet, 6 feet to 5 feet, 7 feet to 6 feet. So we're just working our way through the lengths there and making comparisons. The odds ratio is different for each successive pair of putts in the actual data, but in the fitted model, that odds ratio stays the same, 0.568. Again, that is e raised to the slope of that regression equation. So one of the things that we can do when we're trying to figure out whether a logistic model makes sense is to sort of ask ourselves whether it makes sense for the empirical odds ratios. Do they seem to be roughly constant, right? And in this case, they're not exactly constant, right? There is some variability there, but it's not a huge amount of variability. And so that's just like when you're doing simple linear regression and you have a constant slope in your model equation, but in fact, every time you increase the predictor by 1 and you look at the sample means, they don't necessarily change by that same exact constant rate.